international journals and conferences with a primary focus on to secure an efficient deployment of IoT applications in distributed computing environments. With these few words of introduction, I would like to invite Professor Hemant Kumar Appat to present on the topic for computing paradigm for emerging Internet of Things applications. Over to Professor. Please, sir.
Yes, thank you, sir. I'm very much thankful to the Institute of Engineers India Salem Local Center for providing me such opportunity to provide a talk on the title for computing paradigm for emerging Internet of Things applications. So first of all, we need to understand why fog computing paradigm come into the picture. As already we have know that cloud computing paradigm is the de facto computing model for different applications. Then what is the need of fog computing? Because of the emergence of Internet of Things applications. So in today's world, recently, if you look into different scenario, for example, smart agriculture, smart healthcare, smart transportation system, these applications are mostly enabled Internet of Things devices. That's why these applications are generated through this device. And most of the Internet of Things application or IoT application, in short, we can say, this application are latency sensitive in nature. Latency sensitive in nature means if the result is provided after a certain deadline, then the application execution has no meaning. That's why fog computing paradigm has come into the picture to provide the computing platform for different IoT applications. So let me introduce the basic concept of fog computing. What is fog computing? First, these are the outline for our today's talk. First, I will give you the introduction, then why it is being used by different academia as well as different industry, that is motivation. Next is objective. Next is the fog computing architecture, how the architecture can be enhanced in order to get the computation faster. Next is how the system model is being proposed and what are the different performance parameter that can be used in order to get the system accessibility. Next is one small methodology I have adopted to check whether the results are comparable or not. Then simulation and result, what are the different simulations environment that can be used to simulate the fog computing environment. Next is conclusion and differences. So let me first introduce what is fog computing. It is a novel computing paradigm or novel computing platform, we can say, which extend the services of cloud computing for heterogeneous IoT devices and have its own unique characteristic. For example, it provides low latency, it supports geographical distribution, it supports mobility, and it has a very large number of computing nodes. This definition I have taken from the paper, which is referenced in 1, 2, 3. And also it is a decentralized computing paradigm, provides a solution to provide a supporting infrastructure instead of being a replacement of existing cloud infrastructure. I mean to say, cloud computing server or cloud computing model is available. It is not the replacement of cloud computing. It is the uh, extended version of the cloud computing. Before, what happens when you suppose a mobile user or suppose a IoT user sends their application request to the cloud computing, because cloud computing means the distance between the user and the cloud server is very high. So sometimes the transmission latency is very high. So most of the applications are not executed on the given time. That's why fog computing paradigm is between the IoT devices and the cloud computing layer. That is, when instead of sending all the data to cloud, it is better to send the data to fog computing layer. So the key features of fog computing are it is able to reduce the latency. It provides improved responsiveness of various real-time application. It supports low communication latency deployment for IoT application, and it is comparatively smaller computational size than for a cloud computing server. It also provides real-time processing and analytics. It supports mobility and context awareness. It optimizes the network bandwidth usage, which minimize the network overhead. So these are some basic characteristic or basic features of fog computing. because fog computing is close to the IoT devices. It is developed by Cisco in the year 2012. So the motivation behind this fog computing is more than 10 billion IoT devices exist in 2021 as shown in figure 2. So this figure shows that most of the IoT devices exist is 10 billion number of IoT devices. So this high number of devices put enormous strain on the system structure in terms of network traffic, in terms of security, in terms of privacy, and in terms of latency for various real-time applications. So when the number of these devices are grows indefinitely, then we need an intelligent computing framework that can easily process this devices or this application with minimum latency, with minimum response time, with higher security and privacy. Second motivation is Gartner research indicates the significant growth in healthcare IoT. And nowadays, if you look into various healthcare devices has come into the market, which provides a smart healthcare monitoring system. And it is expected that it will be nearly 52 billion USD by 2028 and USD 54 billion by 2029. So if you look into this data, then we can say that the growth rate of healthcare IoT devices is being increasing. It is also predicted, it is also estimated that by 2025, the healthcare IoT device will account for 39% of the total IoT devices. So the healthcare system can be improved by using IoT-enabled healthcare system, by using advanced computing paradigm, fog computing paradigm. Next motivation is the global IoT in healthcare market size accounted for USD 53.64 billion in 2024, which is grew up to 65.03 billion in 2025, and it is also predicted that it will around 368.06 billion by 2034. So representing a healthy compound annual growth ratio of 21.2% between 2024 and 34 as represented in the figure 4. So these are the figure I have taken from different research articles or different website. This figure represent the growth of IoT in healthcare market size is reported by 2034. So IoT next is IoT enabled healthcare is expected to register a healthy compound annual growth rate of over 23.17% during the forecast period of 2021 to 2026. So these are the some reasons why we are adopting towards the fog computing paradigm, because we need a scalable computing architecture. Because when the number of IoT devices or number of IoT application those increases, in that case, how the computing paradigm will behave. At that time, the computing paradigm should able to provide sufficient number of resources to this number of increasing devices. That's why fog computing come into the picture. So these are the some motivations, while there are many other motivations well the researchers and academia are using for their research. But for my research and for my publication and other things, I have considered these are the motivations, because we can use this fog computing paradigm into different domain. For example, IoT healthcare applications, IoT enabled agriculture system, IoT enable a smart city. So there are many research domain which we can apply this fog computing to provide the services to this high number of IoT devices. The primary objective of this study, or we can say the primary objective of our study, is to develop a decentralized controller. Decentralized controller means, for example, let us consider in any of the city, there are different area. Each area represent a cluster. In that cluster, different groups of IoT devices or different groups of user send their application request to some controller node. So here the objective is to design a controller which has the capability of processing various type of healthcare data or various type of IoT data while ensuring adherence to the standard quality of service requirement. So the standard quality of service requirement, it is taken from one of the research paper. So if you are considering a healthcare application or healthcare services, the QS requirement of each of the services are different. For example, if it is a healthcare monitoring system, that is a telephone system like telemetric system, if a person has some issue related to health, then he can avail the facility through audio. In that case, the data rate must be 4 to 25 kilobyte per second, and delay should be in between 150 to 400 milliseconds, and packet loss is considered and not more than 3%. So these are standard quality of service requirement of various healthcare services. Similarly, in case of video related, video means suppose a monitoring system is there, a doctor is connected to the patient through the video call. In that case, the data rate must be in between 32 to 384 kilobyte per second, and QS requirement, that is delay, is 150 to 400 millisecond. Similarly, the packet loss must be less than 1%. And third is electrocardiogram, ECG related healthcare services can be availed, and their QS requirement is different. For example, in case of data rate, it is 1 to 20 kilobyte per second. In terms of delay, it is maximum 1 second, and the packet loss must be 0. There should not be any type of packet loss during the electrocardiogram services. Similarly, file transfer, if a person's try to send a particular file to the healthcare service provider, in that case, the data rate must be very high. There should not be any delay. There should not be any packet loss. So the overall objective of the research is to develop a centralized controller. Centralized controller means we should have an algorithm that intelligently map the application request to the available for computing node. So how this can be possible? So this is the IoT healthcare application scenario where the data can be generated from different sources. For example, the medical images, medical records, environment data, through internet and social media, different types of healthcare data can be generated, or different types of healthcare data can be sent to the for computing layer. Similarly, wearable devices, for example, smartwatch, a lot of things are nowadays come into the market, wearable devices, mobile phones, similarly genomic data. These are some of the sources where data can be generated, and this data need to be processed by the fog computing service provider to provide minimum latency and high response time of different applications. So what are the challenges of IoT applications? Next is, this application requires stringent quality of service requirement, which includes low latency, high reliability, and real-time responsiveness. So in order to get this low latency, high reliability, and real-time responses, the fog computing, the resource optimization is very important, or it play a significant role for providing such type of services. Second challenges is security and privacy. How to handle the security and privacy issue. If you compare the fog computing service provider with cloud computing service provider, because the security and privacy module is again controlled by third-party providers. That's why some of the users cannot trust over the third-party provider where the data are being sent, where sensitive data is transmitted and processed across distributed fog nodes. So again, it is one of the challenges in IoT application scenario, how to handle the security and privacy requirement of different applications. Next is, IoT environments are mostly characterized by massive scale of connected devices and large volume of data leads to scalability challenges in fog computing. That means the high increased number of devices makes fog computing is a challenge, because fog computing has a limited computing resources. We need some algorithm that intelligently map the IoT data to the available fog computing node for their further processing and executions. So next is fog computing architecture. What is fog computing architectures? Many authors, many researchers have their own architecture for processing or for executing the IoT application. So this talk, or in this our research area, we have considered a 3-layer fog computing architecture. At the last layer, or we can say the bottom layer, is a IoT devices layer. This IoT device layer can be converted into some application domain. For example, Internet of Healthcare device layer, or sometime it will be Internet of Agriculture device layer. It can be Internet of Vehicles device layer. So at the bottom layer, different IoT devices layer are there. These IoT device layer are connected through the fog gateway that is called as IoT gateway. Sometimes fog gateway and IoT gateway are same. This gateway have some computational capability, which again which again offload the data to fog computing layer for further processing and executions. So the fog computing layer is a decentralized and distributed computing layer. Each of the in the given diagram, fog cluster 1, fog cluster 2, and fog cluster 3, we have considered three different clusters. In the fog cluster 1, it is used for a particular geographical area. Fog cluster 2, it is used for particular geographical area. Similarly, in fog cluster 3, it is used for another area. Similarly, these all fog computing nodes are connected to the cloud computing layer. When a particular user sends some application to the next higher layer, that is fog computing layer, if the resources is available, the controller node will decide where the application will be executed. If the resources is not available, then again the controller node will send the application layer to cloud computing layer for further processing. That means the cloud computing layer is work like a backend for different applications. So we need to categorize the type of applications, whether it is a latency sensitive, whether it is a computation intensive, whether it is a IO intensive. Based on the characteristic of the applications, the controller node will decide where the execution should take place. So the IoT device layer consists of various heterogeneous IoT devices having varying capability. Means each of the IoT device has made up of different manufacturing unit. So they can be they can have their own sensor which have no computational capability or less computational capability, and which have restricted computational capability. That's why we need a computing paradigm for their application execution. Next layer is the fog computing layer. It consists of heterogeneous nodes that is called as fog node, and each of the fog nodes support different virtualization technique. This layer leverages various virtualization technique. For example, container enabled technology, Docker and Kubernetes can be easily deployed over the fog computing node to deploy and manage the microservices closer to the data source, enabling real-time processing of various IoT data. Next is the cloud computing layer of the architecture. It consists of various resource-rich data centers. These are enough resources. They have enough resources to present and run all type of tasks, whether it is latency sensitive or computation intensive. But the main drawback or the main limitation is that latency is substantial as distance is large. That's why these IoT applications must be executed in the fog computing layer. So now next is how the fog computing layer can be virtualized, or how virtualization can be built upon this fog computing node to provide different execution environment. So there are two different approach, two different virtualization method can be employed over this fog computing node. First one is called as VM-aware fog computing node, and second one is called as Docker-aware fog computing node. In VM-aware fog computing node, what happens? So in VMware for computing nodes, there will be a fog node. On the top of fog node, there will be one host operating system, and hypervisor is one of the software that can be deployed on the host operating system to provide different guest operating system. So in this case, fog computing node is considered as number of virtual machines, VM1, VM2, VM3, and VM. N number of virtual machines can be deployed over a single fog computing node to provide different execution environment. In contrast to VMware fog computing node, another advanced virtualization method is Docker-aware fog computing. In this case, the fog node have their own virtualization layer. On the top of this virtualization layer, Docker engine is deployed. Docker engine provide different containers to provide the application execution environment. So there are two different methods in this research. We have used virtual machine, or we have used hypervisor to provide the different execution environment for the IoT applications. This is one of the advanced method. So in the next research paper, we have decided to go through this Docker Ever for computing. So VMware for computing node is illustrated in figure 7a, that is first one. It's represent a more traditional virtualized paradigm. Each application or service operates within its own dedicated virtual machines. Conversely, in case of Docker Ever for computing node, as depicted in figure 7b, look into the figure B, Docker Ever for computing node. It utilizes containerization technology, specifically Docker for application deployment and their management. So rather than encapsulating all the full operating system for each application, containers share the host operating system kernel. So what are the research challenges of fog computing environment? The first research challenges is minimization of transmission and computational cost. What are the different methods where we can minimize the transmission cost and computational cost? Similarly, minimizing the energy consumptions, because energy consumption is again a very hot or research area. If you look into the data, uh, if you look into the data provided by different data center, the energy is one of the major research challenges, because data center uses more electricity than entire countries. It is given by it is taken from one of the source, that is Enerdata IEA. So look into this figure. The electricity uses of data center between the year 2010 to 2030. So energy consumption is one of the burning issue when we are developing a computing paradigm. So the objective is to minimize the energy consumptions. Next challenges is lack of uniform standardization. Till now, because it is developed in the year 2012, so the standardized simulation environment standardization is lacking. That's why research on this area is going on. Third is data privacy and security. Again, because when you are sending some application data to the fog computing layer, this data consists of very sensitive informations. So how this fog computing environment provides secure storage of sensitive informations? That is again a challenge. Next is scalability, how the system will behave when the number of applications both increases. That is, there are two type of scalability is considered. One is called as vertical scalability, and second one is called as horizontal scalability. So let me again discuss what is horizontal scalability and vertical scalability in context of VMware for computing. We can consider, let us consider a scenario. Suppose some application request is generated and it is sent to the fog computing node or fog computing layer. In that case, consider 100 applications requests are coming. In that case, if it is able to provide the different virtual machines to 100 application, then we can say that it is scalable architecture. If it is not able to provide the services to 100 application, in that case, we can say that it is not scalable. So in order to provide the scalability, on-demand resource processing method should be employed. What happen in case of scalable? So in that case, vertical scalability means if we are able to increase the computational capability of each of the virtual machine, then it is called as vertical scalability. Whereas when we are able to provide more number of virtual machines during the runtime of application execution, then it is called as horizontal scalability. So most of the researchers use horizontal scalability as compared to vertical scalability, because vertical scalability is considered as more complex, because you cannot increase the computational capability of each virtual machine during the runtime. So these are some of the challenges of fog computing environment in context of IoT applications. So next is what is the definition of IoT applications, or how an IoT application can be defined. So this definitions we have considered in our research paper. This application is proposed. This application is defined by us only, because it can be considered as a software as a service. Like it is a software. IoT application is a software which can be considered as a finite state machine, or sometimes it's called as finite automata, which can be represented A equal to xi, sigma, delta, capital T, and lambda D, where xi represent the non-empty set of finite tests. Means there, if an application, that means an application have some number of finite tasks. And sigma is representing the set of all possible tasks generated through various sensor or IoT devices. Next is delta is a transition functions, which is defined as delta equal to xi into sigma, which tends to xi into sigma, where delta Tij dj is equal to Tij plus 1 and dj plus 1, which represent the output of the input data item. Dj using the function Tij, producing a new data item that can be transferred and processed by the successor task. That means, and D represent the data held by an IT application, and lambda D represent the deadline, if any, fixed by the application developer. So IoT application is a we can say that it is a software like things. It is a finite state machine. So in context of a computing environment, we consider some number of applications, that is A1 to AM, finite number of application requests generated by different IoT device in a particular instance of time. And it is further considered that each application has finite number of tasks which can be represented as Ti equal to Ti1, Ti2 up to Tim. It is also considered that each task consists of IoT data measured in million instructions. This task may be activated on a periodic way or a continuous basis, depending on the type of IoT applications. A sample of IoT healthcare application workflow is presented. So this is one of the healthcare application that can be considered for our research. So it is called as IoT application workflow. Workflow means it is represented through a directed acyclic graph. So this is the directed acyclic graph. So first task is Ti1. It is represented as the entry task because it has no dependency. Ti1 will first execute. In order to execute the second level, that is Ti2, Ti3, Ti4, Ti5, and T6, the prior condition is Ti1 must be executed because Ti1 is dependent on Ti2 is dependent on Ti1. Similarly, Ti3 is dependent on Ti1. Ti4 is dependent on Ti1. So in order to execute the second level of all the tasks, first entry task must be executed. Similarly, if you look into the level 3, that is Ti7, Ti8, and Ti9, the prior means the predecessor task must executed before. If the predecessor tasks are not executed, that means the successor task will be not executed. Similarly, at the last, the exit task, that means which have the out degree is equal to 0. That out degree, if you consider in as a data structure, so the node which have no outgoing edge, that is called as exit task. That means the out degree is equal to 0. So this is one particular healthcare applications workflow. Similarly, IoT application workflow can also be designed in this way. So in order to get the execution of this DAG-based application, first we need to sort this DAG. So how to sort the given DAG into the linear order? The answer is topological sorting. The topological sorting algorithm can be used over this DAG to convert this graph into the linear order. So the system model, so first is IoT device layer. As we have defined in the architecture, the bottom layer is IoT device layer. Let us consider there are different sensors, S1, S2, S3, with a set of sensor with different function are attached to the human body. We are considering a healthcare scenario. Suppose a patient is there, and the patient body, there are 3 different type of sensor deployed on the human body to analyze the contextual data, biosignal data, and temperature data respectively. So by using these 3 number of sensors, what are the possible generated data can be possible? The answer is the power subset of the given set. That is, the data can be generated from one sensor, that is S1, data can be generated from the sensor number 2, data can be generated from sensor number 3, or data can be generated from both S1, S2, data can be generated from S1, S3, data can be generated from S2, S3, and data can be generated from S1, S2, S3. That is, if we have n number of sensors, the number of data can be generated is equal to 2 to the power n minus 1. This is simple mathematics formula. We are calculating the power set of the given set. So 2 to the power n minus 1, if a person has 3 number of sensors, that means 7 different types of data can be generated. Similarly, if you can assume if a person has 10 number of sensors, the number of data generated is equal to 2 to the power 10 minus 1. 2 to the power 10 minus 1 is very high. 2 to the power 10, that is 1024 minus 1, that is 1023. This number of data will be generated at particular instance of time in a particular geographical area by single users. So we can assume if there are more number of users, how many data can be generated in a particular time. So the fog computing layer, it is further consists of different fog computing node represented as F1, F2, F3 up to Fj, where each Fj belongs to fog computing layer, supports type 1 hypervisor to provide a heterogeneous set of virtual machines represented as VM1, VM2, VMI3, and VMIK, where each VMs on the fog node Fi is characterized by following attributes. First one is the processing capacity in terms of gigahertz, the processing capacity of virtual machines, the available memory in terms of GB, storage capacity of the virtual machine. State IK represent the current status of the virtual machine, whether it is in running mode or whether it is in idle or failed mode. Similarly, task IK, task currently assigned or scheduled to the virtual machines or container. For these attributes facilitates dynamic scheduling, resource provisioning, and efficient workload management for various IoT healthcare applications. Next is the cloud computing layer is modeled as a set of heterogeneous cloud server represented by CS1, CS2, CS3, and CSJ. Each cloud host CSJ can run multiple resource intensive tasks in parallel order. A single host can deploy more than one container or one VM to execute multiple tasks in a parallel fashion. So these are the system models which I have developed for measuring the performance of a computing layer. Next is what are the performance parameter. So when you are developing such system model, then what are the performance metric or what are the performance parameter that need to be considered? So there are many performance parameter. For example, max span in context of DEC-based application workflow, it is defined as total time required to complete all the tasks in the given workflow. So the formula, the equation that can be used to calculate the max span is equal to maximum of finish time. And finish time of task I can be computed as FTI is equal to STI plus CI. Similarly, the speed up ratio, the ratio of sequential execution time to parallel execution time is called as speed up. The sequential execution time calculated by using this formula, speed up is equal to minimum of Pj to P, C computational Ti Pj, Pj represent the server, and Ms is the max span. Next is how efficiency can be find. So efficiency of the given workflow is the number of processor utilized. The efficiency of DEC-based workflow can be computed using this equation 3, that is efficiency equal to SU speed up divided by number of virtual machines into 100. Next is schedule length ratio, that is SLR. The normalized schedule length is calculated in order to comparing the performance of scheduling algorithm in DEC using equation 4. Similarly, the energy consumptions of the given for computing node can be calculated from the given equation. So the equation is taken from one of my research paper, which is available on the Google Scholar. So these are the equations which can be used to find out the energy consumptions, the total energy consumption of a computing layer. So next is, let us consider a problem that is called as IoT task placement, or sometimes called as IoT application placement. So the objective function of the problem is to minimize the minimize the maximum cost and execution energy consumptions. See, this omega 1, omega 2, and omega 3 represent the user defined weights. For example, for a certain moment of time, if a user want to minimize the max spend, then omega 2 and omega 3 will automatically considered as zero. Similarly, if certain time the user want to minimize the energy consumption, in that case, omega 1 and omega 2 will be zero. That means omega 1 plus omega 2 plus omega 3 is equal to 1. If you set omega 1, omega 2, omega 3 is equal to 0.33, that means this problem become a multi-objective optimizations. So because the unit of max span, cost, and energy are different, we have used a min-max normalization scale to normalize the given value in between 0 and 1. The min-max normalization is x dash is equal to x minus x min divided by x max minus x min. This normalization method has been employed to convert the given value into the range of 0 and 1. So the objective function minimizing m plus c plus e, m is equal to max span, c is equal to cost, and e is equal to energy, subject to the following constraints. This is the objective function, and it is bounded by some set of constraints. Constraints are given as xij is equal to 1. It represents that the task will either uploaded to the fog computing layer or either uploaded to the cloud computing layer. So when the task is offloaded, that means it must be executed for a single computing node. Similarly, xij ri must be less than equal to rj max. That says that the computing resource requirement of each task must be less than the available resources. Similarly, lij must be less than lij max. That means the latency must be less than equal to the maximum latency. Xij is considered as binary variable that can be taken as either 0 or 1. The next is this placement problem, or we can say that allocations of tasks is considered as NP-complete problem in nature. That means when we are studying computer science or any uh, algorithmic behavior, one term is there that is called as NP-complete problem. So there are two types of problem in computer science. One is polynomial type problem, and second one is non-polynomial type problem. Non-polynomial type problems are those problems which has the time complexity of 2 to the power n. So in order to prove whether the problem is an NP-complete problem, it must establish a relation whether it belongs to NP class or NP-complete problem. The first step is to demonstrate that the problem belongs to the NP class. If we are able to find the complexity in the form of 2 to the power n, then we can say that the problem comes under the NP class. And the second steps involves showing that problem is as difficult as a non-NP complete problem through a reduction problem. So the detailed discussion of NP completeness proof is provided in our recent article. This is the recent article published in one of the Q1 journal, Simulation Modeling Practice and Theory. So those who are interested to solve the problem in non-polynomial NP complete problem can refer those article to find out the solution of different NP class problem. So the methodology, topological sorting, the topological sorting algorithm is used to convert the DAG into the linear order of the DAG. So this is the algorithm we have used to convert. Next is different type of placement approaches has been implemented. First is called as fast fit placement. Fast fit placement says that tasks are assigned to the first available resources that meets their capacity requirement. It is a very simple greedy approach that minimize the assignment time but may lead to suboptimal resource utilization. So these algorithms provide suboptimal solution, not optimal solutions. That's why people, most of the researchers use advanced meta-heuristic algorithm. Next is best fit placement. Each task is allocated to resources that leaves the least residual capacity after assignment. This method improves resource usage efficiency by tightly packing tasks into the resources. Next is a very common approach, that is round robin placement in the operating system. We have also studied the round robin task scheduling. Tasks are assigned to the resources in a cyclic manner. It's, each of the tasks has some time quantum. On that time quantum, the task need to be executed. If the time quantum fails, then the task will be outside the queue, which disturbing load evenly regardless of individual resource capacity. It ensure fairness but may not account for task-specific requirement. Last one is a random placement. Tasks are assigned to randomly selected resources that have sufficient capacity. It is easy to implement, but it lacks determinism and can result in poor load balancing. So the algorithm for first fit is given here. The input of the algorithm is set of tasks and set of resources. So for each of the tasks, first it has to compute the if RJ has sufficient capacity to execute the TI, then assign TI to TI to RJ. Next is next algorithm is first fit. Next is best fit placement. The best fit placement algorithm, we have considered residual amount of, that means the residual capacity is computed using RJ capacity minus TI requirement. If residual is less than minimum residual, then minimum residual is equal to residual, and best fit will be calculated. So on the basis of residual resources, the task will be assigned. Next is round robin place. Next is round robin placement. Round robin placement, we know that each of the tasks has given some time quantum. Based on the time quantum, task will be allocated to the resources. And last one is a random placement. So the random placement for each task in the TI, randomly select the resources from the given available resources until RJ has sufficient capacity. So there are some, these are the some conventional algorithm we have implemented. So based on the algorithm, and it is further uh, simulated using different configuration. These are the configuration we have considered. So number of tasks is 20 to 3000. Task size is equal to 1 to 10B, and CPU requirement of each task is 100 to 800 MIPS, and the execution time is 0.5 to 3 seconds, and task type is workflow based DAG. So from the figure, energy consumption is computed for different approaches. So we can easily conclude from the given figure that the best fit algorithm provide least energy consumption among other approaches. In the figure 9, it is represented. Resource utilization, again, it is resource utilization. Random allocations have lesser resource utilization, and the resource utilization is maximum in case of best fit. That means from the given set of application or given set of configuration, it can be concluded that best fit algorithm performs better than the existing or state of the art algorithm. So further, the execution, if you look into the figure number 11, execution cost is again least among the other method by using best fit algorithm. So max_min is also compared along the different approaches, and we found that the best fit algorithm, the max_min is less. So based on the result, we can say that best fit is performing better as compared to other state of the art algorithm. But this is not the end. We can further optimize this max_min, execution cost, energy, and other parameter by using some different algorithm. So the conclusion is first fit and best fit operate on greedy heuristic that optimize the placement locally without considering the global impact on overall system performance. So these algorithms are not designed to simultaneously handle conflicting objective. For example, minimizing max span and energy simultaneous. Round robin and random election do not adapt based on the resource availability, workload type, or task urgency, which reduces their effectiveness in heterogeneous file system. Next is, as the number of tasks and node increases, the performance of this heuristic degrades significantly in terms of optimality and execution efficiency. This is the limitations we need to consider for some advanced heuristic algorithm or meta heuristic algorithm in terms of optimality and in terms of execution efficiency. So the future work can be meta-heuristic algorithm, which significantly explore the larger solution space as compared to greedy. Meta-heuristic algorithm, the exploration and exploitation leading to better convergence towards the global optima. Further, this meta-heuristic supports multi-objective environment, make them suitable for minimizing the maximum energy and other parameters. So future research can focus on various hybrid meta-heuristic integration with machine learning and real-time adaptive scheduling in the fog-based IoT system. So these are the some references. So these are the some journal which we have published on this area, meta-heuristic algorithm, service placement, that is fault-aware service placement, blockchain-assisted fog computing model, and a comprehensive review. These are some standard Q1 journal which we have published on this area. So people, those who are interested, can go through this paper for better understanding the problem, nature of the problem, and for their solutions. Thank you. Thank you. If you have any questions, then I'll be happy to answer the questions.
So thank you, sir. It's
Is there any
really a
queries, sir,
wonderful
please?
session.
Thank you very much.
Also, more informative, sir. Arun, sir.
Sir, shall we conclude?
Yes, sir.
Hello.
Yes, sir.
Okay, well then. Now it's time to thank everyone who have made this evening a memorable one. First of all, I would like to thank the chairman, IEI Salem Local Center, and the Honorary Secretary, IEI Salem Local Center, for organizing this event systematically, consistently, and effectively for the benefit of the engineering society. I am much privileged to thank our chief guest, Professor Hemant Kumar Apet, for his presentation on the current theme for computing paradigm for emerging Internet of Things applications. Thank you very much, sir, for your presentation. And I definitely think your presentation would have made us more knowledgeable in this topic. Thank you very much, sir. It's my duty to thank the members of Engineers Talk team, Dr. A. Kumaravel, sir, Dr. R. Satish Kumar, sir, and Engineer K.S. Selvam, sir, and IEI Salem Local Center Office Executive Engineer T. Tyagu for their support for organizing this event in a better way. I thank one and all for their contribution in making this event a memorable one. Thank you. Thank you very much.